not C. So for this to fail, B has to fail and C has to fail. You can get by with one of them, but it will fail if only a quarter of them go. What does the and mean? Multiply. So you got the probability of not B multiplied by the probability of not C. What's the probability that B fails?
I think it was 50-50, isn't it? 0.5.
No.
0.7.
No. No. Probability that B fails. 0.2. Probability that it works is 0.8, so the probability that it fails is 0.2. And what's the probability of not C?
0.3.
0.3. So this comes true as 6%. So there's a 6% chance of the second component failing, and that happens when they both fail, B and C. So if this is the probability of the second component failing, what is the probability that the second component is fine? 1 minus this. So if this is 6%, what will the answer be? 94%. So the parallels are like your backups. And so we're left with the probability that the system overall works is the probability that component 1 works and component 2. What's the probability that component 1 is reliable? 0.9. And what is the probability that component 2 is? We just calculated 0.94. And it comes out as 0.846. Now the alternative for calculating the reliability of component 2 is down there, but I don't like it. So it's B or C, which is B plus probability of C, but you must take away the probability that they're both reliable. I think this is definitely the way to go. We'll do one more, I think. Yeah. We have to do quite a lot tonight. I'll try not to rush, but I have to do as much as I can. Reliability block diagram is given for two systems, system 1 and system 2. Determine the two reliabilities and hence identify the most reliable system, where these are the things. Intuition is probably difficult here because I would say this one should be more reliable without looking at the reliabilities. So this one, if one of these works, you're true, and if one of these works, you're true. It's hard to say. Here, pardon?
They're kind of the exact same when you look at it.
Well, they're not.
When you have two R's, you can go A, or B, or C, or else they choose 3 to get you on the first, and then you only 1 in the second. So either or get you through, and then on the other side you have 1 or 2 in the first and 1 or 2 in the second. So it's kind of the same.
Kind of the same. They should be close anyway. See, this one's kind of good because if D, you're straight through.
That's insane.
But if D fails, you have to get through 3 of them. Say, I mean, you can have D failing here. It's probably easier. You have to get through 1 less. So we'll see. I don't actually know. We'll just have to calculate. So the first component, so we'll look at S1. We'll split it up as this being component 1, or a single component, I should say. And we'll just call this component 2. And we'll look at the probability of this failing. Now, how could, now we won't necessarily do it like this, we'll try to do it a bit more natural, although it's perfectly okay. It's saying the probability that this is reliable is 1 minus the probability that it fails, and it fails like this. But I think it's easier probably just to go a bit more direct So what's the probability of not system 1? So what's the probability that system 1 fails? And remember, this is a single, so you just got two components. So how does this fail?
Not C1, not C2.
Not C1 and not C2. Not C1 and not C2. So that's how this is going to fail. So we need to look at C1. So now we can't find, it's a bit difficult to find the probability that C1 fails, but it's easy to find the probability that it actually works. So we'll look at the probability of C1 working. What do we need for C1 to work?
A and B and
A and B and C. What does and mean? Multiply. What's the probability of A? 0.9. B and C is 0.8. Comes out as 0.504. Okay.
Not C1 then is 1 minus that.
Spot on, yeah. So the probability of not C1, so that's C1 failing, is 1 minus that. 0.496. So we've done two things. We said system 1 is going to fail if C1 fails and C2 fails. We know the probability of C2 failing. What is the probability of C2 failing?
not D.
That's probability that it
Oh,
works.
sorry, 0.9.
0.1.
0.1, yeah.
So here we're going to we'll come in with that in a second. So yeah, let's see what we got. So altogether, the probability of not system 1 is not component 1. So the probability of this failing, we found the probability it works. So the probability of fail, we took it away, 0.496. And C2 failing, probability of C2 failing was 0.1. So it comes true as 0.0496. So that's the probability of the first system failing. How do you find the probability that it works, therefore?
Yeah, just this.
1 minus, yeah. So the reliability of system 1 is equal to 1 minus this. 9504. So you need some clear thinking. You definitely want to bunch things together into components. Say, well, if it's parallel, what you do is you calculate the probability that it fails. So you need C1 to fail and C2 to fail. C2 to fail is handy enough because it's just D. D works with probability 0.9, fails therefore probability 0.1. So not C2 is no problem. You need to calculate the probability of C1 fails. It's easy to find the probability C1 works. All three of them work. The and means multiply. You get it to around 50%. So therefore the probability that it fails is around 50% here as well. And so for the probability of that failing, you need C1 to fail and C2. So here's the C1 failing, here's the C2 failing. So you get it. There's a small chance this fails. Take away from one, there's a big chance it's reliable. So that's the first one.
You know, JP, if you see what you done with D there, there was 1 minus 0.9.
Yeah.
If you done that for A, B, and C,
Well, you
would
see,
that still have worked like?
no, because how could this fail?
Well, like A will, there's 0.3 of a chance there.
So what you're finding is the probability that what you're suggesting is going to find the probability that they all fail. But they don't all have to fail for this to fail. That can fail, that can work and work.
Oh, yeah, yeah.
Work, fail, fail, work, fail, work, fail, work, fail work.
Yeah.
So it's a nightmare going that way. Okay. So now we've got more components. So I've got x's and y's and stuff here. We'll probably just ignore this. So we'll cut this up into natural components, this one and this one. So when will system 2 work?
A or C and B or D, isn't it?
Yeah, that's the big show, but if you just put it into 2 components,
C1 and C2.
C1, they both need to work. So this is the reliability of C1 and C2, and the and will mean multiply. So how do we find the probability that C1 works?
Probably have C1 working, isn't it?
Yeah.
Not A and not B.
So that what you're given there, yeah. So
Not
what
A
you're going to do
and
is you're going
not
to
C.
find the probability it fails, and then take one away. So what we're going to do first actually is find the probability that C1 fails. That's not C1. It fails when A and B fail. So this is probability of not. Now just for space, if I do not A and not C, what does the and mean? Multiply. So it'd be not A times not C. What's the probability of not A? Probability of A failing? Yeah,
1.
0.1. Probability of C failing? 0.2. So this comes true as 2%. So we know the first one is 98% reliable. And probability of not C2. So C2 fails if B and D both fail. So again, just for space, we're going to do not B. So not B and not D, and means multiply. What's the probability of B failing?
3.
3. And D failing?
0.1.
0.1. So that's coming out as 3%. By the way, if you give me the right answers, I'm just giving you all the marks. But I think you're better off writing some notation to kind of clear out what your thinking is. Now, whether it's slightly different to mine, that's okay. And what I probably don't like is stuff like not A equal to 0.1. That's not really right. It's a probability of not A equal to 0.1. But if I see the right answers down the bottom, I'm just going to give you all the marks. So if you're kind of struggling with all the notation, don't be too worried about it.
Is there any way of doing a 3 or something like we done in the last one? To make it
No,
easy,
because
reading.
no, there'll be too many. See, this just when it's series, it's straightforward. Like it's just one tree.
Yeah.
They're all multiplied together. But for the knots, it's just easier to calculate the knots. So if I find probability it fails and then flip that. So the second system is reliable if the first one is and the second one is. What's the probability that the first component, I should say, is reliable?
0.98.
0.98. How did you get that?
1 minus 1.
So this probability that the first component fails, 2%, so it's 98% is the probability that it works. And you also need the second component to work, which should be 97%. And this comes out as 0. Geez, they're very close. And in fairness, that was a good shout. they are pretty much exactly the same. Yeah, I don't really have anything clever to say about that. Is D good?
D is 0.9, so
D is very good.
0.1% is going to fail, so
Yeah,
logically you would just say if D works, you're true.
you're true, so it should be quite high just on that. And the second one is high because they're both parallel. Okay, fair enough. Right. So the tree diagram in this are important. Most years they're in question 1. Okay. Right. Now we're moving on to something a little bit different. So the tree diagram. So the tree diagram is connected with conditional probability, and this is connected with your ors and ands, and or situations. You look at them both failing. Ands is a bit more direct. You look at them all working. So it's kind of testing different things, really, I suppose. Now we're moving into, we were talking about random variables originally when we started probability. We're going to start talking about random variables again. Okay. So basically the situation, we're going to have 3 types of random variables, and you'll want to get a feeling for them. Now the first one, the binomial distribution, is you're going to have so many things on trial. Is the thought. So you're going to have n objects on trial. So you're thinking, typically with a binomial situation, you're basically testing a sample is kind of what you're looking at. Testing a batch or a sample. So for example, it might be something like, look at a box of 100 resistors and asking the question, so the random variable would be how many of them are faulty. So you've got n objects on trial, they either pass or fail, they either faulty or not. And the question would be, what's the probability that, say, out of the box of 100, that 3 are faulty, or 3 or more are faulty, or 2 or less. But you've got a finite number of things on trial. That's your rough idea for these. Okay, so example I have here is plants growing in a tunnel. 5 plants in the tunnel, and suppose you have probabilities for each plant that the probability that it grows to maturity is 0.8, and the probability of death before maturity would be therefore 0.2. Or this could be something like some kind of low quality electrical device that a load of them are faulty. What would be an example of something that doesn't tend to be well produced and often faulty, do you know? Cars.
Anything from China.
China, okay, so Chinese resistors. So there's 5 Chinese resistors. The probability it's good is 0.8, the probability that it's bad is 0.2. Just kind of, and you've got 5 of them. You haven't tested them yet. So suppose X is the number of mature plants in the glasshouse. So it'll be the number of, out of the 5, number of good resistors, good Chinese resistors. And the question would be, how do you calculate the probability that there's 3 good resistors out of the 5? Something like this. So if you label the resistors of the plants, say 1, 2, 3, 4, 5, you could look at a probability that, say, the first 3 plants live and the last 2 die. So you got 3 good resistors and 2 bad ones. So this is one specific event. We assume that the mortality statuses of each of the plants are independent. Now that's a dodgy assumption, but for the resistors it's quite good. That the batches, that basically, if you've got 5 of them, maybe they've been produced from all different machines and everything. There's nothing saying that it's not like a bad batch. Each of them has an equal chance of being good or bad. So if you're looking at this event and you're saying independent, this and this and this and this and this, what does and mean? Multiply. So the probability of this happening, the probability of this, multiplied by the probability of this, multiplied by probability of this, multiplied by probability of this, multiplied by probability of this. And the plant growing to maturity are having a good Chinese resistor, 0.8, 0.8, 0.8, 0.2, 0.2. And you've got this. But that's only one possibility. There's loads of other possibilities that you have 3 good resistors and 2 bad ones. So if I kind of show some of them. There should be 10. So now I'll try a few of them. I'll fall after a while. So maybe, let's see, maybe the first two are crap, and the rest of them are good. Maybe the first one is good, then you get two crap ones, and then you get two good ones. Maybe you have a good one, the two crap ones, and a good one. Maybe you have a crap one, a good one, a crap one, two more good ones. You could have good, crap, good, crap, good. You could have good, crap, good, crap. You could have crap, maybe you don't need to take all these down. Crap, good, crap, good. And you have crap, no, good, crap, good, crap. And I think there's one more possibility.